Hello everybody, and welcome back to my crash course in formal logic. In the second part, we're going to be studying inferences, both deductive and inductive. And for those of you who muscled through the first part of this course, you know that this is genuinely a crash course. We're going to cover about 2 lectures worth of material in one single web address, so give yourself time to rewind and review. Now, in lesson number 1, we learned that logic is the science of argument evaluation, and we defined arguments and its constituents, such as premises and conclusions and inferences, very precisely. And just as importantly, we looked at the topic as to whether or not a passage even contained an argument or not, which was pretty much equivalent to whether or not the passage or conversation involved an inference or an inference claim or not. But now we're ready to go into more detail. The 2 key elements of an argument are always, are the premises true, and to what degree do they support the conclusion? And logic analyzes the second of these 2 key issues. Now that means that logic is actually the science rather of support than truth. What we want to know is whether the premises support a conclusion. Whether or not those premises are true is a different issue. Alternatively, you may say that logic is the science that evaluates inferences instead of truth. Logic cannot tell you whether the premises or conclusion of an argument is true. It can evaluate the link-up between the premises and the conclusions. Now this departs from a usage of the term logic that you may find in everyday talk, maybe one that was picked up from Mr. Spock. Consider the argument, all Vulcans are cannibals, Captain Kirk is a Vulcan, therefore Captain Kirk is a cannibal. If Spock thinks that this argument is illogical, it's because he's using the term logical as a synonym for rational, but we're going to redefine that term. What I want to consider is whether or not the conclusion would follow if Captain Kirk was actually as the premises assert him to be. So let's take a look. The first premise said that all Vulcans were cannibals, right? So I'll just scoot the Vulcan class inside the cannibals class. And as the second premise says, Captain Kirk is a Vulcan. Does it follow that Captain Kirk is a cannibal? Notice, by illustrating the premises, I was forced to illustrate the conclusion. So, in a sense, this argument is logical. I guess the sense in which it's logical is one that even Spock could appreciate. He'd at least have to admit that the premises already contain the conclusion. To illustrate it a different way, if somebody says there's a squirrel in my shoebox, and furthermore they add that the shoebox is in their closet, do you know whether or not there's a squirrel in their closet? Well, the answer is already given away, right? Now, what we've encountered here are 2 examples of a type of logical support that's referred to as deductive, because there's no possibility of the conclusion being false and the premises are true. That's because the conclusion is somehow contained in the premises implicitly already. But there's another type of logical support that we need to investigate. Inductive levels of support involve premises that merely raise the odds of a conclusion, although the conclusion is allowed to go beyond what the premises explicitly warrant. Now, I'm going to adjust these definitions in a second, but let's just examine the types right now. Since philosophers like to use illustrations involving ravens, I'll not depart from that venerable tradition. Let's take a look at some deductive support for a conclusion. How about ravens 1 through 4 are all black? And let's add that ravens 1 through 4 were each distinct, and we cataloged 4 distinct animals. Doesn't it follow that there are at least 4 black ravens? In fact, that conclusion follows deductively. It can't be false if the premises are true. But you can't count every animal under the sun, so typically all you get is inductive support. You may say that ravens 1 through 4 are all black, and if you're a really diligent scientist, maybe ravens 5 through 10,000 were black. And all those being distinct animals, you can reach the conclusion that all ravens are black only through a leap in logic. You get some evidence for this conclusion, 10,000 bits of evidence in fact, but the conclusion does not strictly follow from the premises. To go back to a deductive type of support, what if we said ravens 1 through 4 were black and we added that 5 through 10,000 were black, and assuming that each raven counted was distinct and, new premise, only 10,000 ravens exist. Alright, now clearly it follows that all ravens are black. After all, we counted every single one of them and cataloged them. But by way of contrast, if somebody said merely that ravens 1 through 4 were all black, ravens 5 through 10,000 were black, assuming each was a distinct animal, and new premise, less than 11,000 ravens exist. What does that prove? Well, it lends a lot of support, though not proof, to the conclusion that all ravens are black. After all, there's just 1,000 left that we didn't catalog. So you get the idea, right? I'm going to put a supportometer to the right. In the first example, we achieved the maximum degree of support for our conclusion that we could get. The premises back the conclusion in such a way that the conclusion cannot possibly be false if the premises are true. But in the second example, in which there were 10,000 ravens counted, well, we got some evidence or support for the claim that all ravens are black, although our supportometer has to drop quite a bit. And in the case of ravens being counted and we added a premise that only 10,000 ravens exist, assuming that we counted them all, the conclusion then is supported to the maximum degree once more. But if there were 11,000 ravens and we only counted 10,000, then notice on my supportometer I dropped the degree of support down just a little bit to leave a little bit of room for error, even on the assumption that our premises were true. That's how support works. So you get the picture, right? There's two types of logical support, deductive and inductive, and quite a variety of degrees of strength thereof. Now, I do want you to bear in mind, and please pardon my pun about bears and minds, this distinction does not amount to the distinction between a good versus bad argument or a strong versus weak argument. All I've pointed out so far is that support for a conclusion comes in two forms, and if you ever want to attack somebody's argument, be sure to understand and make your attack appropriate to the degree of support the argument intended to offer its conclusion. Having said that, after we know how to recognize arguments, like in the last lesson, we have to figure out which type of argument we're dealing with in any situation. One little bit of help is the use of indicator words. When people say necessarily, certainly, or absolutely before their conclusion, clearly they're trying to do a deduction. In other cases, they may use the term probable, improbable, plausible, implausible. In those cases, what they're trying to say is that the premises made the conclusion more likely. That's an attempt at induction. But once again, we have a problem. In the last lesson, we learned that indicator words were not reliable in distinguishing arguments and non-arguments, premises versus conclusions. So can you rely on them to distinguish deduction and inductive support? And for my 2 cents, the answer is this. No way you can. For one thing, missing indicator words, as in the last lesson, are the norm. And that's true when you're dealing with an argument in a paragraph or in a premise-by-premise form. For example, we used an example involving a frog early on who reasoned that he shouldn't cross a road. Now, that conclusion was reached inductively on the basis of two premises, but notice our hypothetical frog never said, "It's merely highly probable I shouldn't cross the road." That little phrase was left out, and generally, but there's a more important reason we have to take a look at. There are such things as bad deductions. A person may say a conclusion necessarily follows when in fact it does not. And Aristotle, who first developed deductive logic by looking at how categories of things related to each other, cataloged good versus bad deductions on the basis of this. So the idea here is that instead of defining arguments in terms of two types of logical support, we should define them instead in terms of types of claims. In the case of a deductive argument, there's a claim by the arguer or argument that there's no possibility of the conclusion being false when the premises are true. Now, whether or not that claim holds up under scrutiny, that's the job of logic to tell us. And similarly for inductive arguments, there's a claim that the premises raise the odds of the conclusion. For example, Aristotle said, "All men are mortal, Socrates is a man. It follows deductively that Socrates is mortal." Notice we're dealing with three different categories: men, mortals, and Socrates, and category logic is Aristotle's baby. But the point here is that this deduction is successful. But now consider this spoof by Woody Allen: "All men are mortal, Socrates is a man, therefore all men are Socrates." The question is Woody Allen doing a deduction? Well, the problem is, if this is a deduction, it's a bad one. We call those fallacious deductions. The conclusion did not follow, not even probably. However, we need to redefine deduction so that it does not refer to cases in which the conclusion follows necessarily. Rather, we'll say the conclusion was supposed to necessarily follow. Clearly, Woody Allen intended to be doing a deduction. The deduction is just a failed one. So again, we're going to define arguments and argument types in terms of inference claims. Now, returning to our original topic, how do we distinguish whether we're dealing with an inductive or deductive argument? A second way is to look at the general form or style of argumentation. Now, when people are relating categories to one another, like Socrates and Woody Allen a second ago, or if they're just appealing to math or word meanings or semantics and other forms we'll discover later, they're always doing deductions. By way of contrast, there are certain forms of argument that we'll cover right now that are always going to be inductive attempts at inference. So let's cover several inductive forms, and by the way, this list is by no means exhaustive. Let's cover generalization, analogies, arguments from signs, causal inferences, appeals to authority, and predictions. And if you need a little acronym to remember my list of inductive argument forms, I suggest the acronym GASCAP, G-A-S-C-A-P. First, let's cover generalizations. Since we already talked about ravens, generalizations involve arguments that move from a knowledge of a sample to knowledge of a whole group. In the case of Snoopy, he tends to be very bad at these sorts of arguments. He says dogs have been howling at the moon for over 5,000 years, and the moon still hasn't moved, and dogs are still dogs. That proves something, I don't know what. Actually, what it does is instead of proving something, it inductively supports the generalized claim that every evening that dogs howl at the moon are going to be evenings where nothing is accomplished. Another popular type of inductive argument form is the analogy. That's when you infer a further similarity between two things based on knowledge or premises about known similarities. It's actually very important in certain fields of science. So, for example, somebody would say, all and only the rats that ate Agent X got sick, and recognize by analogy that humans and rats have very many relevant similarities, and draw the conclusion from these two premises that if I, a human, eat Agent X, I'll get sick. However, this is an inductive argument. How do you know that humans don't have special immunities that rats lack, or perhaps the rats in the study were already sick to begin with? That would certainly weaken our inference to the conclusion. However, in this case, I think we have enough information in our premises to draw the conclusion that we shouldn't be eating that Agent X, right? Inductive arguments can be very persuasive. I should also hasten to mention that arguments from analogy are very important for moral thinking. Here's a little cartoon illustrating, or perhaps suggesting, an argument that the mascot, the Cleveland Indians, is probably not ethically appropriate. By analogy, would you use a different ethnic group to be the mascot of the Cleveland team? And I use this argument. This is actually a store located in Columbia, Missouri, not far from where I did my doctoral research. Liquor, guns, and ammo. No joke. Well, by analogy, if liquor, guns, and ammo were to be perfectly ethically responsible, wouldn't monkeys, matches, and dynamite be an equally legal and ethical name for a store? I think the two stand or fall together on the basis of similarities. And you may even find analogical thinking in the Bible. Some of you may recall a story where Jesus heals the withered hand of a man and does so on the Sabbath. When he's challenged on it, he claims people would have done the exact same thing if it had been an animal stuck in a ditch. They'd have helped out on the Sabbath. So there's some analogical thinking going on, whether or not Jesus was arguing from analogy or not in that early chapter of Mark's Gospel. Now, arguments based on sign are another very popular form of inductive inference. That argument proceeds from knowledge of a sign to knowledge of the thing that is symbolized by the sign. For example, you see a wavy road sign and you infer that there's going to be curves in the road ahead. The jump from the sign to the thing signified involves an inductive or merely probabilistic inference. The same thing goes when you look at your speedometer and see a certain reading and infer that you are actually going that speed, or even at your timepiece. You see what it signifies and you infer that it is in fact that time of day. Well, to see that these involve some sort of inductive risk, all you have to ask yourself is, how do you know, for example, that a jokester didn't put the road sign there to fool passersby? And how do you know that your speedometer and timepiece are working correctly? Typically, we don't double-check that constantly. And that's the nature of induction. There's always a risk of moving from truth to falsehood when you move from the premise to the conclusion. Now, causal arguments are a very popular form of inductive argument and a very important one. They occur when you move from knowledge of a cause to knowledge of an effect, or conversely from premises involving knowledge of effects to knowledges of a cause. This latter case I promised to come back to in an earlier lecture. Knowledge of an effect and taking that as a leap to knowledge of a cause is sometimes called inference to the best explanation. It happens an awful lot, especially in sciences. For example, Sir Isaac Newton had a certain effect, like the ocean tides rolling in at night. That was an explanandum, something we were actually quite dumb about until he offered the answer, or explanans, that it was due to a gravitational force, that's the cause of the ocean tides rolling in, the gravitational force holding between the moon and the waters. So the move from an effect to an cause is very important in science. And actually, it's kind of important in comedy, too. Gary Larson likes to give you single-panel cartoon strips and see if you can look at the effect here and guess the cause. If you can't, then you don't get the joke. Here's another example. Effect, right in front of you. Can you guess the cause of this? And others, comics like to make fun of people who are really bad at making this sort of inference. Lorna suggests here that doesn't it seem strange that the cleaners would shrink all of your pants? Her husband apparently had the wrong explanans for his explanandum. And I guess that's just due to a self-serving bias, and on occasion we're all guilty of it. Now, arguments from authority involve cases in which you make an inference based on the statements or authority of an authority in a field, say science, or a witness to an event that you were not present to see. Now, in those cases, you are making an inductive leap. It's amazing how often we do this. How, for example, do you know that water is made of H2O or that the ocean tides roll in due to gravity? How do you know when the pyramids are built? Or how do you know when the Constitution was written? Even your local news reports and the inference that you make towards situations really occurring in the world are cases in which you rest your inference on the presumption that the authority can be trusted. Predictions are another case in which people take inductive leaps in logic. Premises deal with some present or past knowledge and move beyond that to knowledge of the future. Even something as simple as the claim, "I will die someday," is based on knowledge that is fallible. I just know that everybody up to now has died, and perhaps we could be saved by science or by some religious intervention and we won't die someday. We're making an inductive leap when we move from knowledge of the past to knowledge of the future. So why would you want to stick your neck out like that? I guess George Santayana said it best. Those who do not learn from the past are condemned to repeat it. So I guess in general, Peanuts characters just are not very good at induction. They're inductive skeptics, I guess. They don't trust generalizations and don't trust predictions. But for people who do such, I guess there's a risk to be taken. Well, congratulations. You've learned a whole lot about deduction and induction and different types of inference and the claims they make, but I want to go into more detail here just as we close. Inference claims are the most important element of logic. They are decided by logic, and if the inference claim is wrong, the reasoning from premises to conclusions is a bad form of reasoning, the argument is junk. And we actually use the strength of the claim of support to distinguish deduction and induction argument types. But I've come up with an acronym to help students wrap their minds about what's involved in various inference claims. A, in the term ANTS, ants, refers to additional premises and whether or not they can add support. In a deductive inference claim, that should not be permitted, but in an inductive inference claim, it's always permitted. So in our example of deductive support for the conclusion that there were at least 4 black ravens, our premises, that we already cataloged 4 black ones, raised our support to the maximum possible degree. You just can't get better than 100%. But we also had an example involving 10,000 cataloged ravens. Now you can add more support to your conclusion that all ravens are black. It's just as simple as going out and counting a few more ravens. And similarly, we had a study in which rats were examined, and on the basis of their similarities, we found out that we shouldn't be eating Agent X. If they got sick, perhaps we will. We had a lot of support for our conclusion, but it could get better. We could answer the following questions. How do we know that humans don't have special immunities that the rats lacked? Or what if the rats in the study were already sick? Answer these questions and include those answers as premises. For example, that Agent X affects organs humans and rats both have, and that the rats in the study were in perfectly good health. Add those as premises, more support for your conclusion that you will get sick if you eat Agent X. Now the N in ants stands for novel information in the conclusion. In a deductive inference claim, there's a claim that there's no new information in the conclusion that wasn't present in the premises. Inductive inferences are sometimes called ampliative because they allow and actually require there to be novel information in the conclusion. So when the premises and the conclusion form a seamless bond, you have deduction. Inductive arguments are the ones in which the premises and conclusion have a gap between them. That informational gap is one of the hallmarks of an inductive inference claim. So let's look at our deductive examples. Captain Kirk, we said, was affirmed to be a cannibal. Why? On the basis of two premises. We said that Vulcans were all cannibals as a first premise, and then we said that Captain Kirk was a Vulcan. Now, there's no new information offered if I say to you that Captain Kirk is a cannibal. That information was already implicit in the premises. Our conclusion just teased it out and made it explicit. Similarly, if all men are mortal and Socrates is a man, the information that Socrates is immortal is already contained in those premises. And similarly, when there was affirmed to be a squirrel in a shoebox and we asked where the shoebox was, well, in that case, when we found out that it was in our closet, you really didn't need me to tell you whether or not there was a squirrel in our closet. The answer to that question and the information in that answer is already contained in the two premises I gave you in black. In an argument from signs, by way of contrast, you actually have to go beyond the information that the sign says thus and so if you're going to reach the conclusion that reality is thus and so. And for that reason, the degree of support that you can achieve in an inductive case is markedly going to be lower than the degree of support you can get from deductions. Now, the T in ants is very important, and we're going to spend a great deal of the course discussing this, whether or not there's a truth-preserving structure or form. Deductive arguments are supposed to be truth-preserving. Inductive arguments are not. What I mean by truth-preserving is that the argument is set up or structured so that truth in the premises will be funneled, if there is any truth in the premises, straight down into the conclusion, and you can take that to the bank. So take a look at the example from Aristotle. It doesn't matter that we're talking about men being mortal. We could just as well have talked about men being Greeks. If all men are Greeks and Socrates is a man, Socrates would have to be Greek. Again, it's not the semantics of mortality or Greekhood, it's the shape of the argument that's doing the work. The same thing holds for Socrates. It's not a matter of Socrates. We could have talked about Aristotle. If all men are Greeks and Aristotle is a man, Aristotle's a Greek. Similarly, our argument involving ravens doesn't have anything to do with them in particular. We could just as easily have talked about bears. If bears 1 through 4 are all black, there's at least 4 black bears. And speaking of which, is there anything special about blackness? How about brownness? If bears 1 through 4 are all brown, and they are distinct bears, that follows there are at least 4 brown bears. Again, deductions have to do with types of inference based on form. And lastly, does support admit of degrees? What's involved in the inference claim in deduction and induction? Deductive inference claims do not allow support to admit of degree. Inductive arguments claims always do. So the way to think about it is that when you're dealing with deductive arguments, the support is there or not. It's like a light switch, on or off, all or nothing on the supportometer. So for example, the claims that all men are mortal and Socrates is a man 100% support the conclusion that Socrates is immortal. And you can't get better than 100% degree of support. But what about the spoof by Woody Allen, all men are mortal and Socrates is a man? To what extent or degree did he support the claim that all men are Socrates? And the issue here is that since he was attempting a deduction, his degree of support failed completely, if it failed at all. Well, thank you guys once again for muscling through another tough lesson, this time on inference claims. If you need a review, just remember your ants. And here's a little cheat sheet just in case you need to go back and do some rememorizing. In the meantime, that's all for now. Wait for my exercises and my next logic lesson. In the meantime, master the ants, and you'll know the difference between inductive and deductive inference claims. We'll see you next time. Thanks for mastering 20 minutes of logic material. Bye-bye.